come to Safari Nursery today to look at color. Wow, these flowers are awesome, Judy.
Absolutely amazing. Can you imagine a world in only black and white? Now, before we start on color, let's do some revision. F is the symbol for the frequency of a wave, measured in hertz or per second. Lambda is the symbol for the wavelength of a wave, measured in meters. Let's also remember refraction. Refraction is the bending of a wave because it has a different speed in different media. When the light travels from a less optically dense medium to one that is more optically dense, it is refracted towards the normal. Remember, the normal is an imaginary line at 90 degrees to the surface. And when it travels from a more optically dense medium to one that is less optically dense, it is refracted away from the normal.
Another thing we need to look at in this module is those calculations we did about the speed of a wave with its frequency and wavelength.
We used the symbol v for speed and derived the equation showing that v is equal to the wave's frequency multiplied by its wavelength.
So, let's get back to color. Now, white light contains all the colors in it, although we can't see them.
Isaac Newton used a prism to split white light into its colors, very similar to a rainbow. You may have played around with a CD like this yourself. This is because the light is refracted.
Red light has the longest wavelength and the lowest frequency, and therefore travels faster through the prism. It is refracted the least. Violet light has the shortest wavelength and the highest frequency, and therefore travels slower through the prism. It is refracted the most. There are 7 colors that come out of white light: red, orange, yellow, green, blue, indigo, and violet. The prism disperses the colors. Dispersion is just another word for separation. You can see that the red light has the longest wavelength and the lowest frequency, whereas the violet light has the shortest wavelength and the highest frequency.
All light and even all electromagnetic waves have the same speed in a vacuum, 3 times 10 to the power 8 meters per second. We use the symbol c to represent this speed. So, in the equation v equals to f times lambda, the v is replaced by the symbol c. So, the equation is now c equals to f times lambda. Let's do a few calculations. Calculate the frequency of red light with a wavelength of 660 nanometers. First, we must change the wavelength to meters. Remember that 1 nanometer equals to 10 to the power minus 9 meters. So, 660 nanometers equals to 660 times 10 to the power minus 9 meters. C equals to F times lambda. Therefore, 3 times 10 to the power 8 equals to F multiplied by 660 times 10 to the power minus 9. Therefore, frequency equals to 3 times 10 to the power 8 divided by 660 times 10 to the power minus 9. The answer is 4,55 times 10 to the power 14 hertz.
Here's another calculation. Calculate the wavelength of light with a frequency of 7,32 times 10 to the power of 14 hertz. C equals F lambda. So 3 times 10 to the 8 is equal to 7,32 times 10 to the power 14 times lambda. Lambda equals 3 times 10 to the power 8 divided by 7,32 times 10 to the power 14. So the wavelength is 4,10 times 10 to the power minus 7 meters.
So, how do we see color? We've just seen that white light contains all the colors in it. So when white light shines on an object, all the colors are there. We just can't see them.
To start off very simply, when we shine white light on a black object, the black absorbs all colors and reflects none. That is why we see it as black. We can say it has subtracted all the colors of the light. When white light shines on a white object, all the colors are reflected, and so we see it as white. We can say it has subtracted none of the colors because all of them have been reflected.
When an object has color, it is said to have pigment. Pigment is a molecule that absorbs certain frequencies of light and reflects others. When white light is shone on a red object, it appears to be red because the red light is reflected and the other colors are absorbed. By being absorbed, they are being taken away from the white light, so we say they are subtracted. Similarly, when white light is shone on a blue object, it appears to be blue because the blue light is reflected and the other colors are absorbed or subtracted. And again, when white light is shone on a green object, the green light is reflected and the other colors are absorbed or subtracted.
Now, when red light is shone on a blue object, the blue object subtracts or absorbs all colors except blue, which it reflects. But there is only red light shining on it, so that will be absorbed or subtracted. As a result, the object appears to be black. Now, when red light is shone on a green object, the green object subtracts or absorbs all colors except green, which it reflects. But there is only red light shining on it, so that will be absorbed or subtracted. As a result, the object appears to be black. In the same way, if blue light is shone on a green object, the green object will look black.
And so it is when light of a primary color is shone on an object of a different primary color. It looks black. Obviously, when light of a certain color is shone on an object of the same color, it will have that color. Like this red light shining on a red object. These objects that do not allow any light to go through them are called opaque objects. Now we get objects that do allow light to go through them, and they are called transparent objects.
For example, we see a red piece of glass as red because it allows red light through but absorbs or subtracts the rest. We see a green piece of glass as green because it allows green light through but absorbs or subtracts the rest. We see a blue piece of glass as blue because it allows blue light through but absorbs or subtracts the rest. So, we say that the color of opaque and transparent objects is seen by subtraction of light.
Now, let's see why the mixing of colors of light is called addition. We use a ray box like this to do the mixing. Colored slides are inserted, and the three lights are created by moving the mirrors. Red, blue and green are the primary colors of light. You get other colors by mixing them.
If two primary colors are mixed, the result is a secondary color. When green and red are mixed, the secondary color, yellow, is formed. When green and blue are mixed, they form the secondary color cyan. And when blue and red are mixed together, they form the secondary color magenta. When they are all mixed together, they give white light.
In light, colors that add up to white are called complementary colors. Now, yellow is made up of green and red light, so all that is needed to add is blue. So, blue and yellow are complementary colors. Cyan is made up of green and blue light, so all that is needed to add is red. This makes red and cyan complementary colors. Magenta is made up of blue and red light, so all that is needed to add is green. So green and magenta are complementary colors.
It is very important to note when colors of light are mixed, they are all there. None of them is subtracted.
This is why the mixing of light is addition. However, usually we create colors with paint or ink. We call this pigment. Let's look at how mixing of pigment works. By subtraction of color, as we spoke about before, pigment works by absorbing some colors and reflecting others. The primary colors for pigment are magenta, cyan and yellow. To produce red, you use magenta and yellow paints. The magenta reflects the blue and red and absorbs the green. The yellow reflects green and red and absorbs the blue. The common color that they both reflect is red.
To produce blue, you mix cyan and magenta paints. Cyan reflects blue and green and absorbs the red. Magenta reflects blue and red and absorbs the green. The common color that they both reflect is blue. To produce green, you mix cyan and yellow paint. Because cyan reflects blue and green and absorbs the red, The yellow reflects green and red and absorbs the blue. So once again, the common color that they both reflect is green. A professional printer only needs to print in yellow, cyan, magenta and black.
Here's a very interesting picture that shows how much of each of the three primary colors of ink goes into making up the South African flag.
Let's try some exercises.
What colors of light are absorbed by a green leaf? Well, green is reflected, and so it must be the other two primary colors, red and blue, that are absorbed. What color of light passes through a transparent green bottle? Only green is transmitted.
Explain which of the three colors, cyan, magenta and yellow, a printer would use to create red. It needs to be the two colors that reflect red, that is, magenta and yellow. Is the answer in 2A due to addition or subtraction of light? It is always subtraction if it involves pigment.
What color of light should a lighting specialist add to create white light if he has to leave a red light on the stage? He needs to use red light's complementary color, which is cyan. Is the answer in 3A due to addition or subtraction of light? It involves only light, so it is addition.
What color light would you shine onto a red object to make it appear to be black? It needs to be one of the other primary colors of light, so it could be either green or blue. Older televisions make use of the three primary colors of light. They are made of thousands of very tiny stripes of red, green and blue. This is an example of addition of light. Have a look at this model of an eye. The light enters through the outer covering called the cornea. Then it goes through the pupil and hits the retina that lines the back of the eye. Cells in the retina catch light rays and change them into electrical impulses. These impulses travel along the optic nerve to the brain, where they are turned into images.
There are two types of cells in the retina, cones and rods. The cones pick up red, blue and green light. The rods let you see on the edges of your eyes as well as at night. It is really interesting to compare the colors that dogs see compared to those that humans see. Lighting specialists that work in theaters and nightclubs use addition of light to create special effects.
Look at these flowers here, they are awesome.
Absolutely.
Ah!
Okay, so I've done it, but now...
Sorry. We've come to Safari Nursery Rhyme today to look at colors.
Nursery Rhyme.